Yesterday we have seen that capacitor stores the energy in the form of charges. Okay, the charge will accumulate on the two plates, positive plate and negative plate. So such that because of charge is accumulating on the plates, one is a positive, another is negative. We can say that it is creating the potential difference. That means some energy is stored in the capacitor. So because of that charged plates, we can utilize for the loads, any type of loads we can connect to it, such that it will, whatever the loads are there, it will consume that charge, and then the total charge will be discharged. Again we need to recharge that battery or capacitor. Now we will see if they are connected in series. If they are connected in series, what will be the, if they are connected in series, what will be the equivalent capacitance? Okay, let us see that two capacitors are connected. Okay, two capacitors are connected. You take the capacitors lines equal length. Okay, not smaller and not longer. Okay, you take two capacitors, they are connected in equal length. I am connecting voltage source, this is positive and negative. Vs is connected. I have considered two capacitors, they are connected in series. Connected in series means end to end connection. Okay, they are connected in series. So if they are connected in series, which law you need to apply? If it is series, if it is series, you need to apply KVL. Okay, if it is series connection, you have to apply KVL because voltages are divided. Voltages are divided. And if it is parallel, if it is parallel, if it is parallel connection, you need to apply Kirchhoff's current law,
KCL.
KCL, because currents divides. Here voltage is dividing. Here what happens when you give the voltage source, the charge will be accumulating on the positive plate. Here the charge will be accumulating on the negative plates likewise. Okay, so voltage drops are taking place across capacitor 1 and capacitor 2. I am applying KVL, Kirchhoff's voltage law. That is Vs is equal to, we know that this is the potential rise and these two are potential drops. So potential drops, I'm writing right side, potential rise, I'm writing left side. Or otherwise, if you want to write in one equation, sum of potential rises and sum of potential drops is equal to 0. That means based upon the charges, here minus to plus, the charge is flowing, and here plus to minus, the charge is flowing. If you want to write, you can write like this also, Vs, that is minus to plus means plus Vs, and plus to minus, the charge is there means minus V1 minus V2 is equal to 0. So otherwise simply I can write Vs is equal to V1 plus V2. That is the thing I have written. This is the one. Okay, Vs is equal to V1 plus V2. And we got that voltages. Okay, we got the voltages as in the capacitor we derived yesterday's class. We derived Vs is equal to what? Vs we got as integration term. For inductor we got what? For inductor we got L di by, for inductor we got L di by dt. But for capacitor, here it is differential term is got, no. If for capacitor you got that in terms of 1 by c integral term, you are getting 1 by c integral I dt. This is the thing we derived yesterday. Okay, that is V is equal to 1 by c integral I dt. So Vs is what? What is V? Here V, total three voltages are there. One V is supply voltage, that one V is Vs is equal to, this is supply voltage, and these two are drops. This is potential rise, this is potential drops. So here potential rise Vs is equal to 1 by c equivalent integral I into dt. Here only one current will be, that means charge is flowing. Okay, charge is nothing, the rate of flow of charges is nothing but current. Here the charge is flowing in the capacitors, that means charges are accumulating across the capacitor, such that the same charge will be accumulating here. No, that means because they are connected in series, the charge will be, same charge will be accumulating here. That is why it is I in all cases. In series the current will be same, that is why I am considering I in all cases. But the thing is, for the voltages it is different, that's why I am indicating V1 and V2 likewise. Okay, so I am writing this first equation and this together as equation 2. I am substituting all these terms. I am substituting all these three terms in equation number 1. I am going to get, that is, let me clear all the, up to here it is over, all of you? Writing part, running notes, it is over or not?
Yes, sir. Yes, sir.
I am clearing all. So here all these terms are there. I am going to substitute in the equation number 1. Equation 2, 3 values are there. I am going to substitute in equation number 1. So when I substitute, I am going to get, that is 1 by C equivalent is equal to, that is Vs. This term is Vs. Okay. This is Vs. 1 by C equivalent, 1 by C equivalent is equal to integral IDT is equal to 1 by C1, not equivalent, it is 1 by C1 integral IDT plus 1 by C2 integral IDT. Okay, 1 by, so 1 by C equivalent, what is common here? Integral IDT, and this integral IDT is common for both. No, I am taking out, that is integral IDT is equal to, open the bracket, that is 1 by C1 plus 1 by C2. Is there any common term left and right side? The left and right side is integral part is common, no? Integral current, I can cancel that value, no? Integral IDT and integral IDT is get cancelled. So I will finally have 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus so on. This is the, that means up to 2 cases, it is up to 2 cases you need to write here. But if they are connected in n terms, n capacitors are connected in series, it is summation of up to that value, whatever the value of n is there, up to that extent it is keep on moving. That means the value will be like this. That what you have observed here, the reciprocal term you have observed. For whereas for resistors when they are connected in series, what we got on R equivalent is equal to R1 plus R2 plus so on. This is the thing you have observed. For inductor, L equivalent, what you have observed? L equivalent, what you have observed? L1 plus L2 suffix plus so on. But only for capacitor, we are getting in terms of reciprocal. That is the difference. That is the thing you need to notice. That is 1 by C equivalent. Just opposite we are getting, no? That is 1 by C1 plus 1 by C2 plus so on. This is the case you have observed. Is it clear, all of you? Only for resistor and inductor they are added, but whereas capacitor we need to do the product by sum. Suppose 2 are there, means suppose if only 2 capacitors are connected, what is the equivalent capacitance? Equivalent capacitance will be C equivalent is equal to product by sum, just like resistors connected in parallel. C1 C2 product, C1 C2 is product, sum is C1 plus C2. So when there are only 2 capacitors are connected, the equivalent value will be this one. So this is the next term you will get after this. After this equation, you will get this C equivalent up to 2 only, no? 2 capacitors only I have considered, no? That is C equivalent. When you do the LCM, you will get C1 C2 by C1 plus C2. Is it clear, all of you? Shall I go with capacitors connected in parallel?
Yes, sir.
Okay.
Yes, sir.
So now let us see that when the capacitors are connected in parallel. Okay. When the capacitors are connected in parallel. See, likewise, parallel connection. You all of you draw this diagram in same length capacitors, not small. Okay. Same length you draw. That is C1. Here it is C1, C2, C3. 3 capacitors are connected in parallel. Okay. When they are connected in parallel, what happens? If they are connected in parallel, different charges will be divided, no? Just like currents, just like, because this is the voltage, not Q4. This is supply mode. I have considered only 3 capacitors. Okay, 3 capacitors, that is C1, C1, C2, and C3. They are connected to a voltage source, that is V and S. Okay, supply voltage, supply voltage. Vs means supply voltage. V suffix. This is capital V, and this will be suffix term. Suffix means down. Okay, so when they are connected in parallel, I need to calculate the equivalent capacitance. So in order to that, here Which law you have to apply? Parallel means what? You have to, if it is parallel, you need to apply KCL. Okay, you need to apply Kirchhoff's current law. When it is parallel, by default you have to go with KCL. So we know that KCL, sum of currents entering is equal to sum of currents leaving. What is the sum of currents entering? This is the node, no? This will be the node. Okay, here this, for this node current is entering. Current is nothing but charge here. Here the charge Q, because of this supply and because of the closed paths, here always current flows from higher potential to lower potential. That means current is flowing from this direction, so it is entering current, that is plus Q. Q is entering. Is there any other currents entering towards this node? Is there any other currents entering when from higher potential to this node? Only one current only, no? So that's why I'm writing only one current, that is Q. Okay, Q is equal to, that is Q is equal to, this will Q or Q equal. Okay, this will be Q is equal to, capital Q is equal to these three currents. That means charges are dividing. That means when it is entering, automatically these three charges will be leaving, no, from this node. One charge is leaving from this path. Q2 is this Q2 charge is leaving from this path, and Q3 is leaving from this path. Okay, total three different paths are flowing. That is Q1, Q2 and Q3. So Q1, Q2, Q3 charges, rate of flow of charges is nothing but current. So based on that, in the case of I1, I2, I3, I am writing as charges. Q is equal to Q1 plus Q2 plus Q3. Okay, Q1 plus Q2 plus Q3. And we know that already have told you that what is the formula you need to remember. Charge is equal to, I have given one
Q is
scientist,
equals to CV.
CV. Yes, very good. Just scientist name you remember, it will be easy. That is CV Raman. That is Q is equal to CV. Okay, Q I am replacing as C into V. Okay, CV I can write. Q is equal to, this is not correct procedure they have made. Okay, this is KCL. Q is equal to Q1 plus Q2 plus Q3, and we know that Q is equal to CV. No, that is Q. Where what is Q here? Q is CV. What is V? V is total voltage. This V is total voltage, and what is C? That is the equivalent capacitance. That is total capacitance. Okay, and the thing is, in parallel, current KCL you need to apply, but thing is voltage is same. No, current is divides. Current divides. KCL applying means what? Current divides. Current divides. Current divides means I1, Q1, Q2, Q3 like that. But the thing is, what is same here? Voltage will be same in all.
Voltage
Okay, voltage is
same.
same for all. Voltage is same. That is why I am writing Vs as for all the cases, because this voltage is applying for this capacitor 1, capacitor 2 and capacitor 3. Okay, so I am substituting Q1 as, I can substitute Q1 as what? Q1 is equal to Q equal to CV. No, what is Q equal to CV? C into V. What is C here at Q1? What is C? It is 1 suffix. What is V? It is Vs. Similarly, Q2,
V, yes.
Q2, C2, C
C2
into V, no?
VS.
C into V, what is?
VS.
That is C2 and Vs.
C2 VS.
Okay, C2 Vs. Likewise, C3 Vs. What is common term here? Vs is common. I'm writing Vs outside.
VS.
Okay, Vs outside. So if you substitute Vs out, if you take it out, you will get C1 plus C2 plus C3. And this Q is what? Q is
C3.
C in C suffix equivalent.
C
Equivalent Vs.
V.
Okay, మీరు ఇక్కడ
Yes.
నోట్స్ ఏదైతుందో అదే నోట్స్ అమ్మా. ఓకేనా, ఏదైతే సమ్ చేంజెస్ ఆర్ మేడ్, యూ జస్ట్ ఫాలో. If I give the notes, some mistakes will be there. You just go through with my notes, whatever the notes we are presenting in the on screen, you just change that one. Okay, yeah. So that's why you need to write the running notes also. It will be easy when you are writing. C equivalent Vs is equal to Vs into C1 plus C2 plus C3. Is there any cancellation terms here? Left and right side. Vs will get cancelled. You will have C equivalent is equal to C1 plus C2 plus C3 only. So if they are connected in n means you need to add that one. Okay. C equivalent is equal to C1 plus C2 plus C3. That means when the capacitors are connected in parallel, what you have to do? You need to summation. What you have observed for resistor and inductor? For resistor and inductor, when they are connected in parallel, we got the values in terms of reciprocal terms. But whereas for this case, that when they are connected in parallel, we need to add. Is it clear, all of you?
Yes,
Is
sir.
it clear? Let me check how much time. Shall I clear all these things? Finish writing part,
Yes.
running. This is the VI relationship. Let us see the VI relationship for this one. Already we got the values. Very, very important. 2 marks. All of you write, make down this table. Copy this table. This is voltage. This is current, not T, it is current. Okay, relationship. VI, or simply they will ask the question like VI relationship for passive elements. They will ask you what is VI relationship for passive elements. Passive elements what? Passive elements are resistor, inductor, capacitor. Okay, resistor, inductor, and capacitor. Serial number కాదమ్మా ఇది. You just make this as element. Okay na? You can observe that serial number is missing here. That is serial number 1, 2, 3, and the element is resistor. You just make the table like serial number, resistor. In the place of element, you write down resistor, inductor, and capacitor. And this table, these values are for voltages, and these values for currents. Okay na? Make heading this as current. This as voltage, and this as element, and this is serial number. Okay, this will be power. P stands for power, and this is energy. Okay, and if you want to add the symbol, you can add symbol last column. You can add symbol also. You can add symbol also. Make it fast. Resistor. All these things already we have discussed. For resistor, V is equal to what you got through Ohm's law. V is equal to
IR.
IR.
Okay,
IR.
by okay, IR you got, that is a voltage. Then next current you can write, no? You can write current from the
I
next.
is equal
So
by
I,
R.
I
this
equal to V
is
by
equal
R.
to V by R. Nice. Then what you got? Power. Power P is equal to product
VI.
of voltage and current, no? That
VI.
is VI.
VI.
Yes,
And
sir.
what about energy? Power into time. Energy is power into time. What is power you got?
VI. T.
VI into T.
VI.
You
T.
just remember like Vellore Institute of Technology. Okay, VIT. Okay, that is energy is VIT. That is Vellore, not VIT Vellore Institute. It is just remembrance purpose I am giving. That is actually V is voltage, I is current, T is time. Now what about what is the symbol now? Symbol for resistor is, draw the symbol, all of you. Symbol also. Okay, up to like this only. Don't draw more and more. If you want to increase, you just variable you can do. But whereas for inductor, coils turns will be there, you have to count. This
Coil.
is
Yes, sir.
just draw neatly. Okay, this is a drawing. I am drawing with mouse, so it is not neatly. Just draw neatly, ma. Coil, you know coils diagram, ma? Turns. Draw it neatly. And what about capacitor? Two parallel plates will be there.
Two parallel. Yes, sir.
Okay, symbol it is. I think already we have derived this one. V is equal to IR, I is equal to V by R. That is the energy and power. Now for inductor, we got a differential term. No, V is equal to L di by dt. Whereas current, for voltage, we are getting differential means current. What you will get? By default, you will get integration.
Integration.
Okay, I is equal to, because from that only we have derived this current. No, I is equal to 1 by L integral V dt. And after that, we derived
VDT.
power. We derived power also. We got power P is equal to Li di by dt. And energy. Energy, how much you got? Half Li square.
Half Li square.
And capacitor, we got voltage is 1 by C integral I dt. And current I is equal to C dV by dt. And power is P is equal to CV dV
CV
by
dV by
dt.
dt.
And half CV square.
Half CV square.
Okay, similarly, just like inductor, half Li square, for capacitor, we are getting half CV square. We got these two equations, no? We didn't derive power. Have you derived this energy? No, no. For capacitor, you can do like this. Capacitor energy, you can find like this integral. For capacitor integral, in somewhere you can write P into dt. What is the P value? Integral P value, how much it is?
CV dV by
dV
dt.
by CV dV by
dt.
dt into dt. Is there any cancellation terms? dt and
dt.
dt cancelled, and C is constant. I am taking C outside. Integral V dV.
V
Integral
dV.
V dV is C
V
into
square by 2.
V square by 2. That is half
2.
CV square. That is the
Half
thing I
CV
have.
square.
Okay. Half CV square is the energy stored in capacitor. This is the value which is going to store. So in next class, we can see the types of sources. Okay, we can see the types of sources. Till now, any difficulty is there? Is the table is clear? I will make it, I will clear all the diagrams so that it will be neat.
Yes, sir.
Yeah, no, write down. Write down all of you. The table is over. You draw that symbols, ma. Draw the symbols for that. Finished all of you?